This is the third and final tutorial on projectile motion. In this tutorial, we are launching things at an angle. And so what we can see is that it is symmetrical and still parabolic in nature. Our vertical motion, first we are going to decrease in speed until we get to the top and reach zero speed. And then the speed is going to increase as we go down, so that as we move over to the right here, we see a decrease in speed, zero speed in the vertical direction at the top, and then increases in speed as it continues over. The horizontal velocity is staying constant, still the same amount, so that doesn't change. And so we get this parabolic shape, which is just like the horizontally launched shape, only in both directions. That's the big difference. So our tips here when launching things at an angle, here we're given a velocity and an angle, so we're going to have to find Vx and Viy using trigonometry, unlike in the horizontally launched projectile where we are given Vx and the initial y is 0. The acceleration is still negative 9.81 meters per second squared, so that has not changed. There is no acceleration in the x direction because the velocity stays constant in the x direction. And just as was said before, if you can't solve for what you need right away, solve for time first, because 4 out of the 5 equations have time in it. So we're going to go through a problem here together. It says during a recent pumpkin flinging contest, a pumpkin was launched with a velocity of 70 meters per second at an angle of 40 degrees to the ground. How far did the pumpkin travel horizontally? And my hint is to think about the change in height of our pumpkin. So first we'll draw our picture, draw our diagram, and we see that the delta x is unknown. Delta y, we land at the same height, so we'll have to keep that in mind when we get to our givens. Then we draw our triangle. Again, only label your distances in the picture. We'll draw our velocity down below. Here it is launched at 70 meters per second at an angle of 40 degrees. So we're going to find Vx and Viy. It is the initial y velocity because this is the velocity at the very beginning, not anywhere else like at the end. So how are we going to solve for Vx and Viy? Well, we'll use our trigonometry. And if I want to solve for Vx, that is the adjacent side, which means it is the cosine. So the cosine of 40 degrees is the adjacent side over the hypotenuse 70 meters per second. Multiply each side by 70, and we get that the velocity in the x direction is 53.6 meters per second. To solve for Viy, that is the opposite side, and so we're going to use the sine. Sine of 40 degrees is the opposite, which is Viy, over the hypotenuse, which is 70 meters per second. Multiply each side by the 70 meters per second, and we get Viy is 45 meters per second. It is up, and so it is positive. That is the only difference between launching at an angle and launching horizontally. Everything else is the same. We write down our givens. What do we know in the x direction? And what do we know in the y direction? Remember, we have two velocities in the y because it is accelerating, but we only have one velocity in the x because it's not accelerating in the x. Of course, we have time, which is in neither the x nor the y direction. So I'll kind of write it to the side over by itself. So first thing, we always know the acceleration, negative 9.81 meters per second squared. That doesn't change as long as it's moving through the air. We're just solved for the x velocity, which is 53.6 meters per second. And here we solve for the initial y velocity, which is 45 meters per second, and it is up, so it is positive. So that's the big difference. The initial y is not 0 anymore. We also know, my hints here, I said that it ends at the same height at which it started, so delta y is 0. Now, believe it or not, we know one other given. Since it ends at the same elevation as which it started. Remember before with free fall, we said that the final vertically is the same as the initial, only opposite. So we actually know the final y velocity in this case. It is negative 45 meters per second. Our main objective is to find out how far horizontally it traveled. We're solving for delta x. So let's go to our equations. We see we have one equation for delta x. So we need to know Vx, which is 53.6 meters per second, and delta t, which we do not know. So as my hints, if you don't know how to solve right away, we solve for time first. So we go to the y direction to solve for time. If I want to solve for time using this equation, I need to know Vfy, which is negative 45, Viy, which is positive 45, and A, which is negative 9.81 meters per second squared. So this is our equation, but it's not the only equation we could use. Understand that we could also use this second equation. Delta y is 0, Viy is 45, and A is negative 9.81 meters per second squared. But out of all the equations, I think the first one is probably the easiest, although it's not the only one. So let's use that one. Vfy equals Viy plus A delta t. We have Vfy is negative 45, Viy is positive 45, A is negative 9.81, and we're solving for the time. Now when we solve for the time here, we first get rid of this positive 45, and you subtract that to the other side. Now the reason I point that out is that because it's a negative 45 minus a 45, which gives you a negative 90, does not give you 0, which some students make a mistake there. So we solve for time. We get the time as 9.17 seconds. And I always like to go back and write that in my chart, 9.17 seconds. So now when I go back to my equations, we need to solve for delta x. I know Vx is 53.6 meters per second, and delta t is my 9.17 seconds. So coming back to my chart here, my equation is Vx is delta x over delta t. Vx is 53.6 meters per second. Time is 9.17 seconds. And we can multiply them to get delta x, which is 491.7 meters. And we put a box around this so that we can quickly determine what our answer is.